let's go to the next set of notes, which is right here. Yeah. Any questions before we move on? No? Good. We got a half hour. Get through some of this. Okay, so we're going to talk about primarily latches and flip-flops and how they're built. So if you want to make something that remembers a latch, the simplest latch is just two inverters back to back. Okay, two inverters back to back. If this is a 1, that's a 0, that's a 1, and it goes back and around, it just remembers where it's at. And if it's the other way around, 0, 1, 0, there's a round and around. Now, that's not very useful. Oh, by the way, if you just had a buffer, you could do the same thing. A buffer with 0 goes around or a 1 goes around. That's not very useful by itself, so usually we introduce some signal in it to make it so that I can set it high or low, because we want to be able to program it. So you can have an OR gate or an AND gate, and this can be a reset. This makes the Q output low. This is a set. If it's active high, it makes the output high, so on. So that's a basic RS latch. And there's all kinds of different variants of them. You can have a set or reset. You can combine them with an AND and an OR to get a set and a reset, or an OR and an AND. And there's different variants of those with active low or active high resets and set. So these are all basic RS latches that you should have learned about in 2607, I believe. And these are just another variants of those, just showing them a different way of connecting them with NANDs and NORs. And these are the symbols for these latches. Now, it turns out that RS latches have very limited use in VLSI. D latches and D flip-flops are the more common storage. So we almost never use these things, okay? Kind of an extra there. Yeah, they exist, but we never use them. We always use these, and we've talked about this a lot. We use D latches and D inputs because they're easier to design and easier to use, okay? And you can have a D flop usually with an auxiliary reset clear, which is used to reset the circuit like shown above. So if I draw a latch like this and it has this R coming in here, that's an asynchronous reset. It resets it irrespective of the clock signal coming in. If I don't have this reset here, if I want to reset it, it'll have to be a synchronous reset. Okay, so the simplest type of D latch that you can make is shown on the bottom here. I have a switch, I have a capacitor, which kind of like acts for the storage, and I have a buffer. And here's the input signal coming on this input, which we don't really call D. Here's the switch, the clock, which is controlling the switch, and here's the Q value. So when the switch is open, where high is meaning open, then the signal doesn't pass through. When it's closed, when it's low, here's signal on the switch, the signal passes through, and so on. So we would call this a transparent low D latch, right? Now, if I just use this capacitor, I get it automatically because this buffer will have an input parasitic capacitance. So all I really require here is a CMOS switch and a buffer, which could be two inverters. Now, and below shows the construction of this. And if I don't even want a buffer, I don't care if I invert the signal. I could just have a transmission gate, right? We did transmission gates, right? I think we did.
Yeah, we did.
Yeah. And we have an inverter to go, so they drive the opposite sides of the transmission gate. The input is a D in this case. This inverter is the output buffer. We're going to invert the signal. We get a Q bar. The capacitance on the input of the inverter acts as the storage capacitance, and that's a D latch. 1, 2, 3, 4, 5, 6 transistors, very simple. Now we call this a dynamic D latch. See this dynamic right here? And it's called dynamic because when we're open and we're holding the old value, so for instance right here, when I'm holding this value of 1, which is stored on this capacitor here, or this capacitor here, it won't stay forever because we know, for instance, these drains and source of this transmission gate, they have these little, whenever we draw a whenever we draw a transistor like this, right, there's these parasitic diodes on the sources and drains, right? So we have this N and Here's our capacitor. Here's our gate. This is a P. Then we have this little EN junctions here, right? And they have a reverse bias leakage current. It's very small, picoamps or something very, very small, but there's some leakage. So this is dynamic. It won't stay forever. So we have to continually be updating this loading in value. So as long as this switch or clock signal is happening at a reasonably fast rate, it works fine. But if I try to stop the clock, it won't work. It'll eventually decay and I'll lose my value of 1.
So for refresh, always, like I know in the case of dynamic memory, we have to refresh it once in a while, but is something that we built into it, or we just refresh it by using it?
You refresh it for like a DRAM. It gets refreshed when you use it, but it also has a little built-in circuit that automatically refreshes it if you haven't used it.
Okay.
Yeah. So an SRAM looks like 2 inverters back to back, storage unit, and then you can write to it. It looks like this, right? So it stores it, and then when this is turned on, you can write or read to it. But it's 2 inverters, so it always remembers it. A DRAM, so this is an SRAM cell, okay? A DRAM cell looks like this. It has a switch, and then it just has a capacitor. Okay? So this takes 4 transistors. This takes 1 little capacitor. So this is much smaller. So DRAMs are typically 4x bigger than SRAMs. And the reason is that they use the same amount of silicon area, but the DRAM is much smaller. But this capacitor, you store a 1 on here, you put some charge on here, and it will decay because there's this little diode right here, right? So inside the DRAM, there's the regular array, but in the corner here will be this little logic that goes through and refreshes this, and it reads it out and writes it back at some very low duty cycle. So since this is going in the background, this refreshing, you can't access them always as fast because there's always, sometimes you get a conflict. So when it's refreshing a cell, you can't read or write it normally. So they're a little more complex to use, and you can't access them always as fast. So SRAMs are faster and easier to use, less complex, but they only have a quarter of the density.
How much faster would you say they are on average?
Say what?
How much faster would you say SRAMs are on average?
Well, they're not super much faster. Like, I don't know what the state of the art is of an SRAM. Depends on the size of it, but they're probably like, what is it? A fast SRAM today, what do they run at? I don't know, 500 megahertz or something like that? I don't know. For one access, so you can get multiple bits in one access. I don't know. DRAMs are like, they're maybe like 80% of the speed or something like that, 50 to 80%, I'd say.
Okay.
It's also more expensive, right?
SRAMs are more expensive.
Oh, SRAMs.
For the same size, it'll be more expensive. So you either pay, if you want the same size, it's more expensive. If you're willing to take a smaller size, then they can be the same cost. And they're more expensive because they just take more silicon area. And that's where most of the cost is of a chip is, remember our 80-10-10 rule?
Yeah.
80-10-10? 80% of the cost is the silicon. 10 is the package. 10 is the testing. So more area, more cost.
I think the cost difference wasn't that much nowadays, but I think that comes back from before. I don't know.
Oh, definitely. Like if you take a 4 gig SRAM versus a 4 gig DRAM, there'll be a big difference in cost. Huge difference. In fact, a 4 gig SRAM will cost the same as a 1 gig DRAM, basically, more or less. Sort of on the same order.
4 to 1.
Maybe it's not quite 4 to 1, but it's on that order.
All right.
Yeah. Anyway, so this is a dynamic D latch. If we want to make our D latch static, then we need some kind of feedback path with something that's driving the node. So below is an example of a D latch that's a static D latch. Okay, so now instead of having a single switch, we make a, what do you call it? Two pole single throw switch. So there's two poles here, and the switch can either connect either one of these poles. So normally when the switch is connected to this one, the top one, the signal's passing through, it's transparent mode, and it's coming back to here, but it's not reconnecting. And then when we switch it to this node, it's not transparent, it's holding it, but now the hold is this feedback path with either two buffers or two inverters. And so it remembers. So yeah, we still have this capacitor that the signal comes on, but we don't care about the leakage. You know, there can be a leakage coming through here, but the fact that it's being driven by a transistor overcomes any leakage on the node. And so this is a D latch with buffers, but the more common way to do it is with inverters. And so now is our input, it gets inverted a second time. So this is the Q output after the second inverter. Does that make sense? Okay, so how do we build that? Well, there's some different ways to do it. One way is those two pole switch, we can do that with two transmission gates. So the two transmission gates, we clock them the opposite way. One is active when clock is high, the other one active as clock is low. So when clock is high, the signal passes through. And when clock is low, the signal loops around. Okay, so the two pole single throw switch can be built with two transmission gates. And if you look at that physically, it looks something like this on the bottom. We have transmission gate. So this transmission gate here is that one, right? The first one. And then we have two inverters. So we're going inverter, inverter. I just put them in series here, and it comes back. It goes through this transmission gate, which is this one. And it feeds back to this node. So this little node here, you can call it X if you want. The X node is right here. And sometimes we add an extra inverter here. The reason we add this extra inverter is that if we take the Q out of here, this is a really sensitive node. It's an internal node. And if we load it, it could affect the performance of the D latch. So often we'll add this one and bring the Q out here. So instead of this feedback path, we'll have a sort of a feed forward path. And so that's a common implementation of a CMOS D latch. And you'll notice we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 transistors in this D latch using transmission gates. And this is the symbol for it. This one's transparent high because this is our clock signal here, right? And so when CK is high, this switch is closed, the switch is closed, and the signal passes through. And when CK is low, we're in hold mode. This feeds back this way. Any questions about that? Nope. Okay.
So is that the absolute way to make a D latch, like the most simplified way?
No, it turns out that's not, but that's the simplest way to understand it.
Okay.
Now we're going to talk about how you really make them. I'm going to draw a picture. So how do we really make them? Well, we really make them this way. We go like this. Bubble in. And go like this. This is our little node X. And this looks like this. And then sometimes we do this. So this is our D. This is our clock. I guess this would be, often we'll go. Clock there. and this is Q. Yeah. So this is how we really make them. And you know what these are, right? What are those?
Tri-state.
It's a tri-state driver, right? We call that our not IF1, right? So inside of that is this thing right here. Remember we spent a bunch of time talking about these, and that's kind of why we did. Every latch uses these inside. So that looks like this. And this one is active high, so that would look like that's kind of like the clock signal. Yeah. Now you might ask, well, why do we do that? Well, first thing to note about this, how many transistors are there? By the way, this inverter here, you don't need it. You can use the same inverter like this. Actually, let's do it this way. You need a clock and a clock bar for this tri-state driver, right? I don't need the inverter because I'm going to have it. So this has 4 here, 2 here, 2 here, 4 here, and 2 here. So what's that? 4, 8, 10, 14. This has 16 transistors. So it has more transistors in it. So you say, oh, why would I do that? It's got more transistors. Well, it turns out the biggest probable reason, there's 2 reasons. One is, unlike the transmission gate version, so the transmission gate version looks like this. Transmission gate, inverter, transmission gate. Actually, there's 3 reasons. Looks kind of like this, right? Draw like that. So the transmission gate, what's happening here is that when we go, this is our D, and this is our clock and clock bar. And then sometimes we go like, this, right? That's cute. You'll notice when the D input goes through, it goes through this transmission gate and then it drives this capacitance. So we kind of have an RC. We don't like that. The reason we don't like that, 2 things. The delay, it adds delay going through this RC, and the timing of it, like the rise and fall times, will kind of depend on, it'll vary depending on this R value. Whereas coming into this gate right here, it's going into these 2 gates, really high impedance, okay? And so that means the timing for this flip-flop is much more well-defined. So that's one drawback of using a transmission gate instead of a tri-state buffer. Another drawback is, let's say this transmission gate, let's say when you manufactured it, this PMOS transistor didn't work. It was a bad PMOS transistor. This thing would still kind of work, right? Because the signal, we know the 0 will go through this NMOS, okay. The 1 kind of goes through, but not very good. So this thing kind of works, but not great. Whereas here, let's say this P transistor broke right here. This thing just doesn't work. If this P transistor doesn't breaks, I can never pull it to 1, okay? So when any of these transistors fail, the thing is dead. And we like that because when we're testing our chip, we don't want it to be kind of sort of working. We want it to either be dead or alive, okay? So this creates a second problem, that it's hard to test the chip to make sure that it totally functions correctly. And then there's a third issue, is it turns out that when you're laying out this transistors, these N and Ps that connect together like this, the layout is not very efficient. And we're not going to get into layout, but trust me to say that this circuit here, where the N's and the P's are on one side and the N's are on the other side, you see here, I have the P's and N's connected on both sides. Here, I only have them connected on one side or the other side. This turns out to be a much more efficient layout, so I can make it more compact. So even though it has more transistors, the layout is more compact, so it takes a similar amount of size. So hence, this is the way we actually build D latches. And flip-flops are made out of D latches, so are flip-flops. So these tri-state drivers we spent a bunch of time learning about, they're in every D latch and every D flip-flop that we put in our chip, so they're important. Okay. So yeah, that's what this next slide, this clocked inverter or tri-state inverter, this is what it looks like. And this is showing how you build that. I don't know, I kind of took this from somebody else's slide. I like my version of it, but this is basically the same thing. It goes into this tri-state buffer, it goes into this node X. So this node X is right here, right? This is my X. And the X goes into an inverter, and the inverter comes back to another tri-state driver, and it goes to this X. That's what mine does. Tri-state driver here goes to inverter, another tri-state driver back to X. I like this drawing better than the other one, to me, in my mind, but they're both the same. And I kind of explained the operation. Pros, it needs a buffer to keep the load capacitor from changing setup time. Yeah, so compared to a transmission gate, this buffer kind of changed, like the setup time and everything is very consistent with because you're always going into this high impedance capacitance. So there's a delay through it, and it changes the setup time depending on the rise and fall time because of this resistor effect of the transmission gate. The input buffer reduces interaction with source resistors to keep the timing simulation uncomplicated. We talked about that. And it eliminates transmission gate testing problems. A transistor failure would cause a fault, not a slow circuit. Yeah. And this is 14 versus 12. I said 16. Well, depends on whether you add this extra buffer or not. If I didn't add that extra buffer out there, then it's 14 versus 12. But in any case, this has more transistors for the clocked inverter version of it, or tri-state inverter version. Okay. Any questions about that? No. Okay, the next thing. What are we doing for time? We got 5 minutes. Let's draw a picture here. Let's. Okay, I'm going to make a D latch. And I'm going to feed that D latch into a second D latch. I'm going to make this transparent high, and this is transparent low. That's CK, D, Q. We're going to call this D. I'm going to call this Q1. I'm going to call this Q2. I'm going to call this CK. And I'm going to draw some waveforms here. I'm going to make, this is my CK. Make a few clock cycles. Okay, and this is my D. I'm going to make, so this is CK. This is my D. I'm going to make D go. Okay, and then we're going to draw Q1. So how does Q1? Q1 works. We have this D latch, and this is a transparent high D latch. So whenever the clock is high, the D will pass to Q1. So let's do that. When clock is high, the D will pass to Q1. So what does the Q1 start off as?
Oh, no.
X, right? Don't know or don't care?
No.
Don't know, yeah. Get that one straight. Okay, so then the clock goes high, it goes low. Stays low here. And, oh, sorry. Goes low, and then it's transparent mode, so it follows that. So then it goes high. And then it goes into hold mode. And it's in hold mode, so it stays all the way till, and this is important, a little bit after this clock edge, it's going to go low when it goes transparent again, right? So just remember, there's a little bit of delay there. That's important. Then it stays low. It's transparent here. So, curious here. Let's just make this like that. So what happened here? It was transparent, high. So then it went hold, didn't see that. So then, it goes high here temporarily, and then it goes low again, right? Because it went low. And then that's high, right? So then it's transparent, doesn't do anything here. Then it goes high here, right? And it stays high. I get that right? That's Q1. So let's draw Q2. Q2 gets Q1 as its input. So Q2, we're gonna get 2 minutes. I'm gonna finish this off. So Q2 is unknown here. And then this doesn't go low until a little bit after that clock edge, when this goes transparent. So for Q2, it's the opposite. It's transparent, but the X is coming through. And then when clock goes high, it's in hold mode, but it was always at X. So it stays X all the way over to here. Right? And then it goes transparent again, and it sees this, and it goes to a 1. Make sense? And then it goes here, it's going from, it's transparent. This is going low, but not till after the clock edge. So it doesn't see that going low. So it stays high here. And then it goes transparent again, and it goes low. And this didn't happen until after the edge again. So it doesn't see that little glitch there. So it stays low. And then it goes transparent. Oh, is that right? Yeah, stays low here. And then this again is after that edge. It doesn't see that. And then eventually, this, when it goes transparent again, it goes high. So that's Q2. Now, the funky thing about this waveform is, so we look at Q2, just ignore Q1. If we just looked at D, clock, and Q2, what you would find is, look, here's where Q2 is changing right here. That's on this negative edge of this flip-flop. And it's changing right here on this negative edge. And then didn't change here, and then it changed here on this negative edge. So in fact, Q2 only changes on the negative edge of clock. And effectively what's happening is we're sampling, this goes high, so this goes high. We're sampling here, this was low, this goes low. And we're sampling here, this is high, this goes high. And actually it was sampling here as well, but this was low, so it stayed low. So in fact, when I put these two latches together, I actually get a flip-flop. These two things together, I can make this into, I can represent it as D, Q, and now I can call this a negative edge triggered flip-flop. So those two things are that. So the way we make flip-flops, and we call it a master-slave, the first latch is the master, the second one is the slave. This is a master-slave flip-flop. It's built out of two latches. And we're out of time, but if that's a negative edge, if I want to make a positive edge, I just reverse this. I make the first one transparent low and the second one transparent high. You can try that out yourself, draw a little waveform and convince yourself. And so all flip-flops are built of latches, and all latches have tri-state buffers. So we use tri-state buffers in their latches and flip-flops. And we ran out of time. Any questions? No?